Did you ever want to know where integrals are even used and how? Well, welcome to 28th lecture, application of integrals. So we know the integral is the area or surface under the graph, so to connect it to today's lecture, we will see how we can use that. I will only mention a few possibilities as a lot more of them are just in math, and I think that I generalize it better, like just presenting the surface. So today's video will actually be shorter, but still good to get the idea where we can even use this concept. So here we have the all familiar sketch, the surface under the graph, showing that the integral of f of x dx between a and b equals to s. So the surface between those 2 points under the graph. Now this is all graphical, so what else can we do on a graph? Well, we can draw another function. So let's say we have two convoluted functions like this. Well, what's integral got to do with this? Well, we can find the surface between the two graphs on certain intervals. So we see that there's space between them here, there's some space here, some space here. So of course, we find the surface between them, right? Well, we won't do it for these two specific functions, as if you saw them, like the writing, the function, you would probably leave instantly. But nonetheless, I can still show you not these functions, just a general rule, since we learned integration last time, but in today's mini test you will have to solve for the surface between two functions, so better pay attention. First things first, you need the interval. Now, here those 2 points for the interval are marked with blue. Now, you could be given these points and you could solve for something like this, but we don't like this, as it's not an entire surface between the curves, because like you could have two nice numbers like exactly 0.25 and 11, but there's still some space left in this segment. So sometimes you will have the entire segment, so the points determining it, given. Sometimes you'll have to find them yourself. Of course, we could do the indefinite integrals, so between minus infinity and positive infinity. But then we would have to make sure that the sum doesn't diverge, so we're back on series and sequences lectures, which I hate, and they will overcomplicate this, so for our sake, we will only be solving for the surface between two functions in this type of closed surface. For that, first we need the 2 points, as I said, so the 2 points in which the functions intersect. Some functions intersect more times, some less. If that is the case, we just choose some vertical intersection at stuff like x equals 0, etc., or manually restricted. I think I will cover an example where this can be handy and used on 3 functions. Yes, I do later on, yes. So, back to the point. We get those two by equating two functions and then solving for x values. So, function of x equals the second function of x, and then solve for all possible x's. Then we just choose the interval. For more complicated functions, there will be more. For simpler one, there will be one. Like on the mini test, there will be 2 intersections. Or 1, and you'll have to figure out why. That's gonna be a fun one. So after we have those points or intersection positions, you need to figure out which one is a top, so which function is above and which one is under. This is sometimes very annoying, especially if they like switch a lot, or if the functions don't give nice values. But if you have 2 consecutive x's for intersections, and you take any x value between them, and then insert that value into both functions, which I marked with red, so I get the result, the y value, which I marked with red. As long as that x is within the interval, they should technically follow that rule along the entire interval, so whichever one gives the highest y value, that one is the top one and the other one is the bottom one, as they shouldn't change that, because if they did, that point would be moved closer and that interval would still have the same rules. So I went ahead and changed the colors to better visualize it. The top function is the red one, the bottom one is the blue one, as you can see here. The integral of red is given, like, is everything under the red function within this limit, and it's colored red. And everything under blue is the surface, or the integral of blue, and that interval is colored blue. So following color theory, however that's called, when blue and red mix, we get purple. Why is that important? Well, using these two integrals, we see that they both share the purple part, ergo the color being their mix, but more importantly, only the red colored part, so the one that didn't mix, is the part of the surface between the two functions in that interval, so the one thing we want to know how to get. So to get it, we would need to subtract the mixed part from the entire part, or in set explanations, for the set of all points under the top graph, we subtract the set of all points under the blue graph, as those mix and we get purple, which we don't want in our red result, if that helps out. So with that logic, let's write out the generalized solving process for the formula. First step is equaling the two functions and solving for all the x's on where they intersect. I have marked that x, the result x, as xi, meaning we can have x1, x2, x3, etc. And then we choose two consecutive ones. This is kind of misleading, as technically xi plus 1 has to be greater than xi, since that will ensure that our sign of the result will be correct. So we will rewrite this as an interval where a is lower and b is higher. Then we find an x value, I will call that xs, in the interval between a and b, where a is obviously lower and b is higher. Then we need to determine which of the functions is the top function, so basically inserting that x, I marked it with xs as I said. For the sake of example, let's assume f of x is the top one, so the red one, and it gives higher y value, so this looks like the emoticon or however that's called. Basically, you check which of these functions gives a higher y value when we insert that same xs from the interval. That one is the top one. So, as I said, for the sake of the example, I will assume that f of x is the top one and g of x is the bottom one. And then we write the definite integral for each of the functions between the values a and b, so our two consecutive x's, or xi's, and take the difference, so subtract the bottom one from the top one. This is important because the sum of the surface matters. Sorry, the sign of the sum of the surface matters. The sign will show us, or the sign will change regardless of where the functions are, either under or above the x-axis. And if our interval contains more than two touching points, etc., so do keep in mind that signs matter and it's important to get them correctly. So the bottom limit will always be the lower of the two, and the top limit will always be the higher of the two, unless the teacher gives specific instructions, and then you subtract the bottom function from the top one. And that's it, that's the rule. It is important to note, you can break down these integrals. I haven't mentioned this last time. Let's say we have another point marked as C, so let me just draw this. This is point A, this is point B. Let's mark another point C. So integral of some function between B and A, like this. I'm getting better at this. It can be broken down as, we know that integral is the surface, so we can break this surface, the entire red one, into two parts. One being this left part, and the other one being this right part. So we can write this as a sum of two integrals. Oopsie. I can't erase that, okay. As the sum of two integrals. And those integrals, if we look where they differ, so how do we ensure that the entire surface is accounted for? Well, the first one is the integral between A and C, and the other one is between C and B. So, like this. In this way, we ensure that our integrals, just like short on space, because I am a bit dumb. So basically this way you can ensure that it's easier to add up. This will be very helpful in some examples, especially in the mini test, because I forgot to show it here. So basically, you can break the integrals like this. This follows the rules and it's intuitive, but you have to hear and see it for you to be able to like know that you can do it. So you can easily break that down, and just keep in mind that's the surface, that's how it works. You can easily break them down apart like this. Hopefully this is clear. If it's not, comment down below, I will explain it again. But now we can get onto the example, the area between three functions. So let's solve one example. I chose an easy one, but it's still relatively complicated. It is recommended you sketch them to get an idea of what's happening and how you should approach it. So I equal the functions 2 by 2 by 2, and we get the following values. So I marked the y1 with y2, and we got the first one, so minus x equals x. That is only true if x is 0. and then I equaled y1 and y3, x equals 2. That only is true if x equals 2. And then I equaled y2 and y3 to get x2, 3. Minus x equals 2, so x has to be minus 2. That's how I got these x intersections. Now I could either sketch it out, or I can do it without the graph, but I'll do both so you guys can kind of see them and get the idea of how it works. The lines are kind of thin, but I did color code them so they fit to their respective functions. As you see, green to green, yellow to yellow, and red to red. So now that we have our sketch, we know which graph is on top and where and how to solve it, because it becomes trivial. But what if we didn't know? What if we didn't have a sketch? Well, as we learned, we take two consecutive x values here, like minus 2 and 0, or 2 and 0, whatever you want, and find a point between them, like x equals 1, which I will mark with the purple line. Like here, x as 2, so I forgot why it's called a 2, I will see that later, is marked with a purple line here. We see that at that x, so minus 1, the green function is the top one, because it gives the highest y value. Yellow is underneath that, and red is on the bottom, so the far bottom. Now we check the other two consecutive points, the 0 and 2, and our x as 3 is 1. So here, we see that when inserting 1 in, we get green as the highest, red as the second lowest, and yellow as the bottom. So here, as we see the graph, it's easy to determine, but if you just have the points and you don't know which one is top or bottom, look for whichever one stays on top. So here, we see that as we change these points between the three intersections, we figured out that one function stayed on top or one function stayed on the bottom, always. Like, these are the two possible examples where we have 3 points. And it's just different rotations of a triangle. Either one function will always stay at the bottom, or one function will always stay at the top. That's what you're looking for. In this example, we see that the y3 will always be on top, so that is always our top function, and then yellow and red change. So in one example, yellow is going to be our bottom function, and the other one, red, is going to be our bottom function. There's a lot of examples that I could make up. Sketches are very useful, but they're not necessary. But they pretty much make it trivial to solve. But yeah, first part will be between the green and the yellow, and between the first and the second x values. So in ascending order that I have reordered them. So between the first and the second x values, we will have the integral between the green and the yellow function. And the second part will be between the green and the red function, between the highest or the last two x values. So let's write this all out. The surface of the integral, like between the three functions, is equal to the surface 2 plus surface 3. I marked them S2, S3 to better fit with the purple lines we use to determine the order. So our surface 2 will be between the points x1, 2, between x2, 3 and x1, 2 of 2dx minus integral between x2, 3 and x1, 2 of minus x dx. So let's color code this a little bit better. So the orange intersection point is on top and the blue is on the bottom, and then the surface 3, which is on the right, is between the orange and the purple. As we remember from when I mentioned before, you can combine the integrals or break them apart. So in this example, we broke apart this entire segment into two parts. As we can see, what is it? Minus 2 is the blue one, so this would be our A, so the lowest one. This is our C, so the point in between. And it then breaks and continues here at C and then continues towards B, because this part changed. Okay, hopefully this kind of clears it out. So we have set our integrals following the formula before. I can insert the values in to make it easier to you to understand it. And now we just solve these. Here I will combine them into the same integral through sum and difference rule, as it will be a lot easier space-wise. I simplify the signs. And now we just integrate one per one, because sum and difference rules means that we can integrate them separately. I just combine it so I save on space. So integrate the first one, we get a constant 2 into a 2x, and then x becomes x squared, then we have to divide with a new power. And then before we finish, because this is a definite integral, we add this vertical line with the limits next to it. And the same for the second example, where only the sign changed, and the limits, of course. So we insert the limits and we do some simple math. Like anything times 0 is 0, so the entire term with this will just, it disappears, and we know that if we want to get rid of a minus, it has to be in the bracket, and as we insert minus 2 as x, and x is squared, that will become 4. So we insert the 0 into the first part and the minus 2 in the second part. We take the difference between this first will disappear, so we're only left with the second part, which remains here. And this is the first part, because the second part is all zeros. Now we just solve for this. This is minus 4 plus minus 2 squared is 4, divided by 2 is 2. Minus 4 plus 2 is minus 2, but there's another minus here, so we're gonna simplify that. Here we have 2 times 2 is 4, minus 4 divided by 2 is 2, so 4 minus 2 here. We simplify the signs here, is 4 minus 2, so we get 2 plus 2. And these are our individual surfaces, and they're 2 units. So putting them into our formula for the overall surface between the 3 functions, we get 4. I overdid it with everything because there's so many colors, but hopefully this was easy to follow, so that we can move right on to examples. Physics. We're back at physics, and when we did applications of derivatives, we said that velocity is the rate of change of position, and acceleration is the rate of change of velocity. So if we turn that around, velocity is the integral of acceleration, and position is the integral of velocity. And that makes sense because if we move with a constant velocity, we can see what distance we covered in a certain amount of time. At a certain time, we have covered the surface underneath the graph of distance. And we know this is our formula from last time. So let's say at time t1, we want to know what distance we had already covered if we were moving at a constant velocity or speed. So from the graph, we see that the distance would be velocity times t1. Now let's use our integrals to determine that. We set the integral between t1 and t0, but since t0 is start and that time there is 0, we just write 0 instead. Now, what are we integrating? We are integrating velocity, but we see that it's a constant. I mean, it is a function of time, but it doesn't change with time, so there's no time variable in it. We could, if it was like linear, that would be v of function of time, because it was dependent on like time. As time changes, so does velocity. In this example, that's not the case because velocity is like a constant, for example, okay? So we will treat this as a constant, and because it is a constant, we use the constant multiple rule, and it's multiplied to whatever we're integrating, so change of differential of time. Because, well, we're solving in regards to changing time, so how does something change as time changes, blah, 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 blah. We're working with differential of time, so we add a dt after velocity, since time just linearly increases. And now that we have our integral, we just solve it. We use the constant multiple rule that I mentioned to move the velocity in front of the integral sign, and we integrate dt, and we know if we only have a differential of a function, that function will be the result. And now that we integrated it, we still have to insert the limits. We get v times t1 minus 0. And since something minus 0 is something, we can simplify it into v times t1. And this is how we get the result using integrals. How cool is that? Well, of course, as I said, velocity is sometimes not constant and then becomes a function. So you cannot move it as a constant, but you have to integrate it over time. So the integral from dt changes to integral of some function of t dt. And then you actually have to know the rules and everything, so that's why it pays off to pay attention in my videos. But yes, we will do that in physics chapter as to not overload you. However, you're free to try and solve this yourselves. Start with actual geometrical stuff, like square plus the triangle, like this is a square and this is a triangle. Wait, I can actually draw this, so this is a square, this is a triangle, and this is like t1. And you have two surfaces that you add up together, and then you get the formula from that. Okay, perfect. It is a nice exercise to train your brain into systematic thinking, so I recommend it a lot. But let's get ahead and show some more examples of where this is in physics, and yes, they will get progressively more advanced. We don't really know this formula yet for work, but for the sake of it, let's say that work is defined as some force when working on some distance. So if you're pushing a block on a certain distance for a certain length, that's the distance in here. Here W, capital W, means work, capital F is force, and X is distance, which is often used in context of springs or coordinates and small shifts, etc. But then again, any marking is accepted if you label it right. I'll explain it better when we learn it, of course, but I'll try my best to give a visualization of sorts. So let's imagine a spring that's fixed on a wall or an immovable object. The other side is free and the red stickman is holding it. Now he wants to extend it to be 2 times longer, so 2 times as long as it is currently. For that he has to apply force, a pulling force strong enough to stretch the spring out. Also that marking on top of the arrow, that's how you write vectors. I didn't include them in the math roadmap because they're a prerequisite for physics, so they will be uploaded among the physics lectures, but will be put in math playlists, so do not worry. But they will arrive when physics starts, so there will be at least a month of downtime. All we need to know for now is that vectors refer to direction and magnitude, but more memes and explanations will come when we get there. So the longer the arrow, the greater the vector value, so in this case, the bigger the force. But now that this is stretched so far, the spring wants to return to its optimal state, let's say the one it was originally in, so the force required even to just hold it is much higher. So in this example, the force increases as we distance ourselves from the starting or resting position. The vectors here represent the force that the stickman is pulling with. As when we get to the lecture, we will see we need to draw the balances pretty much always, because we will see why. But yeah, setting that aside, we see that as x increases, so does f. Meaning that our function of... Oh wait, I draw that, never mind. I forgot. Yeah, this allows us to draw a graph. The force as a function of x, it starts at some value because, well, you hold it. And then it increases as x increases, so the distance. With springs, there is a thing called Hooke's law, basically about the force being directly or linearly proportional to distance of displacement. But more on that when we get there. For now, we see that we have another change of something, of some function as its variable changes, so another integral, which funnily enough is the integral of f of x dx. But yes, there were some easy examples, so let's get into one a little bit less linear. So, a flow-through pipe. For simplicity's sake, let's ignore all the details and fancy words and just sketch it out. How does a water flow in a canal or a pipe? Usually like this. We know that the flow at the center will most often be the fastest, and the flow near walls will be slower due to friction and every other effect that you can imagine. So how would we determine the actual flow, like the speed or the volumetric flow of this water? Integrals. The sketch already shows it since I put it up right so it's more similar to a graph. So I set a graph of flow as a function of distance. In reality, it would be easier to explain it if I set the y-axis in the center of it. So I could mark this as the radius. So the coordinate system would be something like this, where this is radius and this is like flow. Let's call it f. So this here would be 1r, so one radius, and this would be another radius. So like that way you can determine, because this is a symmetrical graph and you can just like isolate half of the system and treat it as a special unit in itself and then just double the result. But yes, this will do for now. Our curve of the liquid front will represent a graph, and the integral of that will represent the added contribution of each individual different flow. To be precise, I would set up the dependent variable as the surface or the cross-section, which is an infinitesimally thin part that we could sum up to form the volume of the pipe, and we would watch the sum of contributions at one of these cross-sections. This is a dumbed-down oversimplification, as I'm not even that caught up with English terminology on this topic and field, so I do apologize. But no better explanation or formulas can be provided other than just visualization that was hopefully enough to get my point across of where we can use it. Correction, where we will be using it, because, well, the formulas are slightly a bit too complex for us at this current point. As for chemistry, there are a few examples, but most notable I would love to point out is the proton NMR, nuclear magnetic resonance. The image is the proton or H NMR of ethanol, so the basic component of all alcohols, spirits. Basically, when you get drunk, this is always present. We will learn what these are in chemistry, but all we need for now are the peaks. These things. Why? Because proton NMR, simply said, is useful for telling us the number, or more precisely, the ratio between different hydrogen atoms, and of course how they're distributed along the molecule, but we'll learn that when we get there. And of course, you guessed it, the amounts are proportionate to the surface, or the integral of the peaks. Let's ignore the number of peaks in each group, that's a topic for another day, years down the line, but their integrals, they, as I said, correspond to the number of hydrogens. Sort of. Why is that the interesting part? Or what is the interesting part about this is that when this technique was first developed, the software wasn't smart enough to do it, or at least to do it fast. So what they did was print out the spectre, cut out the peaks, and weight them. So they converted surface into mass and used ratios between the mass to determine the results. I don't know, it just seemed like a fun fact to point out, how you can combine relatively difficult concepts like integrals, summation of infinitesimally small parts, with some logic and creative thinking to find a way to solve this problem. So you're literally counting the ratio of hydrogen atoms in a molecule, or different hydrogen atoms in a molecule, and you determine that by weighing something, weighing a piece of paper. That's kind of fascinating. Since I don't study economics, I don't really know that much about this topic, but the formula I found was that the total value of stuff like stocks or something is the integral of investment times the rate through the differential of time. I don't think this is the entire formula or that it is exactly right, but I do believe it's somewhere in the right direction, as your total is the sum of all that you have invested with a certain rate that adjusts for the actual value of what you're investing into, and then integrating that over time so as the value or rate or investment changes. I don't know, I don't study that topic. This is just here to show that integrals aren't only in science and mathematics. Integrals can also handle shapes with no formula as well. As many real-world shapes and objects do not have simple designs and geometrical formulas that they would follow, we can use integrals to determine the shape's area or surface, its volume, or its length. Of course, we don't integrate the function, but we do break down the shape into vertical or horizontal slices, break down the area into simpler shapes, use cross-sections, etc., and then add up those values. How is that done? I do remember our professor talking about a method for the volume of some shapes. They take an image, determine the size ratio of image to IRL, and then manually outline the objects, take several pictures to make a 3D render, then slice it into thin layers and then just add them together. I don't know how, because again, I'm a chemistry student, but yes, you can do a lot with integrals, as we will surely see in physics chapter. Honorable mention, do not bother trying to learn about this. This is just here if you ever see an integral sign with a weird symbol. This is a contour integral. Since normal integrals are integrated between 2 points, this monstrosity is doing the integration along a full path, not just an interval. That path can be along the circle circumference, for instance. It's basically a loop. So this is an example, truly a frightening sight, don't you agree? But yeah, we will probably only see these when we're covering Faraday's or Gauss's law, and of course Maxwell's equations, but we won't use them. I'll just show the formula with them, and I'll use the normal ones because, well, why would I complicate this? This is just an example, though. Basically, if normal integral works on a straight interval, so something like this, then contour integral goes around. And yeah, basically, that's all you need to know, is that they account for the loop and stuff like this. Basically adding up values in the loop, so up to the center this rotation is added together, as opposed to the interval where we use normal integrals. So yeah, the contour one appears in electromagnetism, just like the top of my head describes how the fields behave. For instance, magnetic fields basically running loops around the wires that have some current running through them, so to measure the total effect of the field, you would integrate around that closed path. I hope this presents it, but it's in no way a must-know thing, just that you know it exists, so you're not scared the first time you see it. And anyway, that was it for the lecture today. This is the mini test. I wish you best of luck. And yeah, thank you so much for tuning into today's lecture. I hope everything went well. I hope you learned something useful. I hope you expanded your horizons. And I'll see you all on our next quest. Bye.